Hi, hello, welcome. This is Discrete Mathematics, and today we're going to talk about Section 2.1, Mathematical Systems, Direct Proofs, and Counterexamples. Chapter 2 in our textbook is all about proofs. We're going to talk about formal ways to prove things. This section is mainly going to focus on direct proofs, which is the most direct way to prove things, so we'll talk about that. But first up, let's talk about mathematical systems. A mathematical system consists of axioms, definitions, and undefined terms. Let's talk about an axiom. Axioms are things that are assumed to be true. They are a foundational starting point in our system. They are the things that make the system make sense. Without them, there would be no system. We are assuming, you have to assume a certain amount of things to be true. You have to have some kind of foundation. Those foundational truths are axioms. From those axioms, you can build definitions. Definitions are used to create new concepts in terms of existing ones. Some terms are not defined explicitly, but rather they are implicitly defined by whatever our axioms are. Within our mathematical system, we can derive theorems. A theorem is a proposition that has been proven to be true. There are two special types of theorems, lemmas and corollaries. A lemma is not a very interesting theorem in its own right, but it can be used to prove a more important theorem. From that more important theorem, we can have several theorems that follow right after that, or that follow easily or directly from that, and those are called corollaries. So lemmas are happening before some sort of big theorem, and corollaries are afterwards. An argument that we use to establish the truth of a theorem is called a proof. And logic, like many of the logical ideas and concepts and tools that we learned in Chapter 1, are the tool that we're going to use for the analysis of proofs. So here we have Euclidean geometry. Euclidean geometry is an example of a mathematical system. Some of the axioms in Euclidean geometry are two distinct points. If you have those, there is exactly one line that contains those 2 points. That's what a line is. That's how points and lines work. It's a fundamental truth of the system. Another one is that given a line and a point, there is one line that goes through that point that is parallel to your original line. That is another axiom in our geometry system. Some definitions. Two triangles are congruent if their vertices can be paired so that the corresponding sides and corresponding angles are equal. So we have this triangle and then this triangle over here. These triangles are congruent if these sides are the same and these sides are the same and these sides are the same, and then all the same thing with the angles. That's what it means to be congruent. Two angles are supplementary if they add up to 180 degrees. So here's 180 degrees. This angle plus that angle is 180 degrees. So alpha plus beta is 180 degrees. That's what it means to be supplementary. So we're defining those two terms. And then using a combination of our axioms and our definitions, we could prove these two theorems. The first one is, if two sides of a triangle are equal, then the angles opposite them are equal. So here's our triangle. This side is equal to this side. We can use these definitions, other definitions as well, to prove that this angle is actually equal to that angle. That's a theorem that we could prove. Another one is, if the diagonals of a quadrilateral bisect each other, then the quadrilateral is a parallelogram. Something like this. So if this and this are equal and that are equal, then my quadrilateral is actually a parallelogram, which means that this side is parallel to that side and that side is parallel to that side, as opposed to something like a trapezoid. Okay, so the type of proof that we're going to talk about mainly in this section is called a direct proof. Theorems often have a form for all the domain. This is the domain for all x's in a certain area, like all positive integers, for example. This is the domain. If p of all those x's, this is my hypothesis, then q of x's. This is my conclusion. So for a certain domain, I have this hypothesis. that it's going to lead me to a certain conclusion. So when we are working with our direct proofs, we're going to say, let's let these values, this variable, be in my domain, and we're going to assume that our hypothesis is true, and then we're going to try to prove that it follows, using the tools of logic, that my conclusion is also true. All right, example 2. First, we have a definition. An integer n is even if there exists an integer k such that n is equal to 2k. So this is what it means to be even. If an integer is even, it can be written as 2k for some integer k. If an integer is odd, then there exists integer k such that n is equal to 2k plus 1. So an even integer, and then you add 1, and then you have something that's odd. The integers alternate between even, odd, even, odd, even, odd. So if you take an even integer and add 1, then you're back to something that's odd. So we have this idea of even and odd. And this 2k and this 2k plus 1 is a structure that we're going to use a lot in these proofs. So keeping those definitions in mind, we want to prove that for all integers m and n, if m is odd and n is even, then m plus n is odd. And we're seeing we could, according to the last chapter, write something like for all integers, for all m and n, we could have some function here where m is odd and n is odd, then m plus n is odd. So we could write in some sort of structure. That's not totally necessary, but if that helps you digest a little bit what's happening, you're free to do that. So for our proof, I'm going to write, this is a proof. Sometimes in parentheses, I like to write what style of proof I'm doing. We're going to talk about more styles of proof in the next section. So I'm going to write a direct proof here. I'm going to start off by assuming talking about the domain and talking about my hypothesis. So this is the hypothesis, m and n. M is odd and n is even. So I'm going to talk about that, and then I'm also going to talk about this. So I'm going to let m and n be integers. Let m be odd and n be even. So I'm going to use logic to prove this conclusion. M plus n must be odd. Okay, so since m is odd, if m is odd, then m is equal to 2k plus 1 for some integer k. Since n is even, n can be 2. I don't want to use the same letter up here because k and l, they can actually be different things. So I'm going to say l. N is equal to 2l for, I could say some integer l, or I could say l in z, which are the integers. Usually I like to pick a style and use that style for the whole proof, so maybe I will do that this time, but those are both options that you could do for some integer l. Notice that, again, this is a different variable. If they were the same variable, then I would be restricting myself to m being the next integer after n. And that's not really part of what I'm doing. I'm saying this works for all m and n, as long as m is odd and n is even. So they could be different. They don't have to be consecutive integers. So this is a different variable. Okay, so now I'm ready to write down. So m plus n is equal to m, which is 2k plus 1, plus n, which is 2l. And that is equal to, let's see, 2k plus 2l plus 1. And I could factor a 2 out of this first set here. So that's 2k plus l plus 1. And this k plus l right here is an integer. K is an integer and l is an integer. So their sum is an integer. I don't know whether, I'm not making any statements about whether that is odd or not, or even. I'm just saying that it's definitely an integer. And now you can see I could replace this with something else, maybe like m. So then I would have 2m plus, well, I can't do m. I could replace it with another letter, but I think I'm starting to see that this is 2 times an integer plus 1. That is the same form as something that's odd. up here. So I've actually proved already. I'm going to say hence m plus n is odd. And I'm going to end my proof with a little square, and I'm going to color in the square. This is called a tombstone. Tombstone, and it is a popular way to end a modern proof. If you read some older textbooks or you encounter some older writings, they'll often have written QED, which is Latin for, I forget exactly what it stands for, but the D is like demonstrated. What we meant to demonstrate has been demonstrated is what QED stands for. That kind of turned into an open square. People wrote that for a while. And then there was a Hungarian mathematician, in like the middle of the 1900s, his name was Paul Halmos, and he is the one that popularized, let's color in the square, and that's going to be the way that we end the proof. It looks kind of like a little tombstone, like a gravestone that you'd stick in the ground. So that kind of stuff. That's how many modern proofs are ended. I like to end my proofs that way just because it feels really satisfying. Like I did it, and I draw a little box and you color it in. It's almost like checking something off a list. So I just find it to be personally satisfying. So that's the way that I prefer to end my proofs. It's definitely a signal that this is the end of the proof. There's no more after this. So you don't have to use the tombstone, but it is something that you'll encounter if you encounter proofs out in the wild. All right. Many students find proofs to be daunting, find them to be quite difficult. And I'm hoping to make them a little bit more accessible. So here's my attempt at doing that. Writing a proof is like telling a story. When you tell a good story, you want to talk about who's the story about, what is happening to that person, give some more plot details, and then in the end, come up with the conclusion to the story, a satisfying conclusion. That's kind of like what we're doing when we're writing a proof. The who is the domain of discourse. So in the last one, we had m and n were arbitrary integers, and then we did some stuff with them. They could be rational numbers. They could be positive real numbers. They could be whatever the domain is. That's who we're talking about in our story. What is happening? This is our hypothesis that you include in your story proof. So that's in the last one we had assuming that m is odd and n is even. Or we can suppose that x is positive and y is positive, greater than 0. So that you could include definitions at this point, but this is your hypothesis and then things that follow directly from your hypothesis. From there, you can talk about what's happening. Now that we've kind of made some claims here, we've talked about the person and what they're doing, we can give more details. So if m is odd, well, then we can write it as 2k plus 1 for some integer k. And then we can hopefully start to relate that to our conclusion in some way. If we say that x is a rational number, then that means that x is equal to p over q. For some integers, p and q can't be 0. That's what it means to be a rational number. So here is where definitions come in here as well. And hopefully we can work out some algebra, some logic, something to do with sets, and we can end up at our conclusion. Therefore, m plus n is odd. So here's some words to help us as we write our proofs. And you'll notice I used a number of these in that first proof that we did together. Let, suppose, assume, first, at last, finally, because, since, so, hence, thus, therefore. These ones are often used near the end of the proof. So, hence, thus, therefore. At the beginning of the proof, we often use let, suppose, assume, things like that. Since sometimes is kind of included in the middle somewhere, or because. This is in that kind of give more details step. So these are some useful words that you can use as you're writing your proofs. And then, like I mentioned earlier, I like to end my proof with the tombstone. It's kind of like you're checking off the box, I did the proof, and it's so satisfying. All right, let's do a few more proofs together. Here we have example 3. Prove that for all rational numbers x and y, x times y is rational. So here we're going to start off with all rational numbers, x and y. That's what I'm going to start my proof with. And I'm hoping to end with, therefore, x times y is rational. Let's see if we can get there. Here's going to be my proof. Let x and y be rational numbers. So if they're rational, what does that mean? That means they can be written as fractions. Oops, that's supposed to be an S. Since x is rational, it can be written x equals P1 over Q1 for P1, Q1 in Z, and also Q1 can't be 0. Can't have 0 on the bottom. That's what it means to be rational. So here we're seeing a definition. I'm going to do the same thing for y. Since y is rational, y is equal to P2 over Q2, different different integers, for P2, Q2 in Z, and Q2 can't be 0. So now I've used a definition to write what it means to be rational. Next up, I'm going to talk about my conclusion. I think I can get there. So x times y must be P1 over Q1 times P2 over Q2, which is P1, P1, P2 on the top divided by Q1, Q2 on the bottom. And this is an integer. The product of two integers is another integer. And this down here is also an integer. And I know that Q1 times Q2 is not 0 because Q1 is not 0 and Q2 is not 0. So the only way to get 0 would be for one of those to be 0. And I said neither of them are 0. So I've proved that x times y is an integer over an integer where the bottom integer isn't 0. That's what it means to be rational. So, or hence, or therefore, or thus, x times y is rational. And ending my proof. And that's it. Let's do another one. Now we're entering the land of sets. We have some sets here. Prove that for all sets x, y, and z, x intersect y minus z is equal to x intersect y minus x intersect z. So let's see. Let's draw some pictures to just make sure that we think this is true before we continue. Here is my universe. This is going to be x, and this will be y, and this will be z. And you know, since I did such a good job with this, let's copy this, and I'll have it again. Okay, so here let's do the left-hand side, this side. So in my left-hand side, y minus z is all of y, but not z. So this part of y, a little cutout from z is missing. And I want to intersect x with that. So x intersect, here's x, so just this part right here. You got it all in orange, that'll stick out better. So x intersect this part right here. So that I'm looking at just this little slice where x and y are intersected, but not the part that also has z. That little slice, that's the left-hand side. Let's look at the right-hand side. The right-hand side is x intersect y. So that's this piece right here. And then also x intersect z. That's this slice right here. And I'm taking this green slice and I'm subtracting off this purple piece. So that leaves this piece right here. Green minus purple is this piece. Okay, so look at that. It is the same piece. The piece that is x and y, but not with z. So I am convinced that this is true. All right, so in order to prove this equal sign, what we want to show is we want to show that x intersect y minus z is a subset of x intersect y minus x intersect z. And then we also want to show, that the subset goes both ways, that the left-hand side is a subset of the right-hand side, and that the right-hand side is a subset of the left-hand side. I want to show both of those. So we're going to have two parts to our proof. So here our proof, I'm going to show this direction first. I'm going to suppose that the left-hand side is true, that x is a member of the element x is in x intersect y minus z. And then I'm hopefully, from that, I'm going to show that it's also an element of the right-hand side. Here we go. Since x is an element of x, because it's in x intersect y minus z, And I guess maybe I'm not since, maybe I'll say so, because it follows from this right here. To be a member of X intersect Y minus Z, it has to be in each of these. It has to be in X and it has to be in Y minus Z. So X is an element of, so small x is an element of the set X, and small x is an element of Y minus Z. To be an element of Y minus Z, that means it has to be in Y, but not in Z. If it was in Z, then it would be taken out in the minus part of it. I'm going to say, hence, small x is an element of Y, but small x is not an element of Z. Since little x is in X, and little x is in Y, little x is in X intersect Y. That's what it means to be an intersect, so it has to be in both pieces. You'll remember that from our rules of inference, possibly. Possibly you remember that, not that possibly it's there. Because, oops, I said sin, and I meant to say since. Let's see, where am I at? Because X is not an element of Z, and X intersect Z is a subset of Z, X is not an element of X intersect Z. All right, so we're ready for, since X is an element of X intersect Y, and X is not an element of X intersect Z, X must be an element of X intersect Y minus X intersect Z. So that is one of the directions that we're supposed to prove. Now we're ready to go the other way. All right, now we're ready to go the other way. Here we are. Let's go this direction. So we are going to suppose that little x is an element of X intersect Y minus Y intersect Z. And we're going to try to show that X is also an element of this left-hand side. So if it's an element of something minus something else, then little x is an element of X intersect Y, but it is not an element of Y intersect Z. Since X is in X intersect Y, that must mean it's in X and it's in Y. Because X is in X, but X is, because X is in X and X is not in X intersect Z, then X must not be in Z. Since X is in Y, but X is not in Z, then it is in Y minus Z. Thus, X is in X, and X is in Y minus Z. So X must be in X intersect Y minus Z. So I think I've proved both directions. So X intersect Y minus Z is a subset of the right-hand side, X intersect Y minus Y, X intersect Z, X intersect Z, and X intersect Y minus X intersect Z is a subset of X intersect Y minus Z, and thus I'm just going to say the equation holds, because I don't want to write the whole thing again. And that is the end of my proof. Okay, we're ready to move on to how to disprove a universally quantified statement. Back in section 1.5, we talked about how to disprove for every x, p of x. All we need to do is find a counterexample, one member of the domain of discourse that makes p of x false. So that's what we're going to try to do here. The statement for every n in z plus, so these are positive integers, 2 times n plus 1 is prime, is false. I want to find a counterexample. So this statement right here is not true, and I want to look for a counterexample. So this is saying that all positive odd integers are prime. And I know that's not true. Let's think of a positive odd integer that is not prime. So my counterexample, you could think of many. Maybe I'll say 27. 27 is 7 times 3, which is not prime. I could think of another one. 9 is 3 times 3. That's not prime. Another one, 25, is 5 times 5, which is not prime. So here I've come up with 3 different examples. You only need to come up with one. So let's maybe use this example of 9, which is 3 times 3, is not prime. So here we go. I'm going to let n equal to 4, which 4 is a member of z plus. So I'm dealing in the domain of discourse. Then 2 times 4 plus 1 is 9, which is not prime. So I could have chosen any of the other examples that I came up with and figured out what value of n leads to that number, which is not prime. So this is indeed false. And here we are at example 6, the last one. If the statement A intersect B union C is equal to A intersect B union C for all sets A, B, and C is true, prove it, otherwise give a counterexample. Well, I'm not sure if this is true or not. Let's see if we can prove this one. Okay, let's draw some pictures. Here's A and B and C. And I guess it didn't paste, so we'll draw it again. Here's A and B and C. All right, so we'll work on the right hand side first. A intersect B is this piece right here. And I want to union that with C. So this is C. So I'm looking at all of C plus this little bit where A and B are intersected. That's the piece that I'm looking at. Okay, so for the other side, I've got B union C, which is all of this. And then I want to intersect that with A. So just the parts that intersect with A. That's this part right here. Okay, so these pieces do not look like they're the same. It looks like this picture on the left includes the rest of C, and I don't have all of C. I just have that part of C that's intersected with A. So these are not the same. So I need to find a counterexample. So what I'm going to do for my counterexample is I'm going to pick a color. I haven't done black. I'm going to say this is piece 1, piece 2, piece 3, piece 4, piece 5, piece 6, and piece 7. So I have 7 pieces. So here's going to be my counterexample. I'm going to use my 7 pieces that I've written down. So for my counterexample, I'm going to let A be equal to, A is 1, 4, 5, and 7. Those are the numbers that I made up for A. B is going to be 2, 4, 6, and 7. Oops, curly brace. And C is going to be 3, 5, 6, and 7. All right, everyone on track so far? Now we're going to look at, well, what is A intersect B union C? That's going to be, let's see, A intersect B is, get my highlighter here, 4 and 7. So 4, 7, union C, which is 3, 5, 6, and 7. So these two united together are 3, 4, 5, 6, and 7. And I'm seeing that in my picture as well. The left-hand side is everything that's there in purple, which is 3, 4, 5, 6, and 7, not 1 and 2, everything else. Well, let's take a look at the right-hand side. This is my left-hand side. My right-hand side is A intersect, that's not a very good intersect, A intersect B union C, which is A, that's 1, 4, 5, and 7. Intersect B union C is 2, 3, 4, 5, 6, and 7. So intersection of these two, let's see, they both have a 4, they both have a 5, and they both have a 7. And I see that does correspond to this picture. This one is 4, this one's 5, and this one is 7. I didn't write all the numbers in here. 1, 2, 3, and this one is 6. So this means that the right-hand side is 4, 5, and 7. And these two are not equal to each other. So this one is false. And that is the end of this section. I will see you next time.